Welcome to our next lecture video on engineering mechanics statics. So for this lecture video, we will discuss about the following topics. So the first one is equivalence of vectors. The second is force and their characteristics. The third one is the moment of a force about a point. And the fourth one is the moment of a force about an axis. So let's start first with equivalence of vectors. So from the fundamental properties of vectors, we can say that two vectors are equal if they have the same direction and magnitude. Because as we all know from our previous lecture, we defined vectors as a quantity that possess both direction and magnitudes. So if there are two vectors with the same direction and magnitude, therefore these two vectors are considered equal. But in statics, the word equal is not the same with equivalence. So these two vectors that are equal to each other may have been, or shall we say, they are not equivalent to each other. So in other words, two vectors may be equal but not equivalent in a certain scenario. So a vector is considered not equivalent if the effects or the response of a body applied to it is not the same. So for instance, if we have a certain body, shall we say we have here a box, and you push the box here with a force P, shall we say the vector or the force vector is directed to the right with a magnitude P, then you have also the same box with the same force P, which is also the same magnitude P and same direction, which is to the right. So these two forces is considered equal because they have the same magnitude P and the same direction going to the right. But as you can see in the figure, the first box may have a different response due to the applied force P compared to the second box that is where the force P is applied in the lower part of the box. So in the first box, if the force P is applied to it, the box may tip like this one because of the effects of the force P applied to it. In the second one, the box may go to the right or slide through the floor because of this force P applied to it. So as you can see, the two vectors is equal, but the response of the body is not the same. Because the reason of that is because the point of application of the force is different. Because as you can see, the force in the first box is applied on the upper side of the box, and the second force here is applied on the lower part of the box. So because of this scenario, we have classified vectors into three major classifications. So vectors based on their equivalence. So the first one is the fixed vectors. So fixed vectors are considered equivalent vectors if they have the same magnitude, direction, and point of application. So the same magnitude, meaning if the force is 100 kilonewton, the other force should have the same magnitude, which is also 100 kilonewton. So the direction should also be the same, and the point of application. So in our example in the last slide, the point of application is different. So meaning it cannot be a fixed vector. The two force vectors are not considered fixed vectors. Next one is the sliding vectors. So sliding vectors are equivalent vectors having the same magnitude, direction, and line of action. So as you can see, this type of equivalent vectors is not concerned about the point of application. So an example of that is the same with last time. If we push a box on a force P right here, so as you can see, the box may slide going to the right, but if we transfer the force at this as you can see, this is what we call the line of action. This is the line of action. If we transfer the force P along its line of action, shall we say we put it here, say we attach a cable on the side of the box and pull the box going to the right. So as you can see, we have the same line of action. So we transferred it from this point to this point and not changing the line of action. So as you can see, the box will have the same response to the force P if you pull it or transferring the force P to the right side, and the response is still the same and the box will still go to the right. So that's an example of a sliding vector. So sliding because we can transfer the force P at any point along its line of action. Then we have free vectors. Free vectors are equivalent vectors having the same magnitude and direction. So these types of vectors are not particular in the point of application and line of action. So a common example of these free vectors are couples, which we will discuss on our next lecture videos. So we will explain that later. Then our next topic is force and their characteristics. So due to direct contact of bodies, the forces arise from it will result in both motion and deformation to which it will act. To understand forces, some of its important characteristics are listed below. So a force is a contact between two bodies which is so small and it may be considered as a point, also called as a point of contact. So if we have two bodies right here that are in contact at a single point, so at this point we have a force, let's say force F, the same to the other body, force F. So as you can see, this point right here, which is also here, which is at this point, is what we call the point of contact. So if the force is acting on a point of contact or on a single point, that is considered a concentrated force. Because on our next lectures, we will also discuss other types of forces like the linear load, or shall we say the uniform load, and or distributed load. Then we also have the pressure or the pressure load. So next one, another important characteristic of a concentrated force is its line of action. So the line of action of a concentrated force is the line that passes through the point of contact that is parallel to the force. So this is the point of contact. So this is the line that is parallel to this force F. So this one right here is the line of action. So that is another important characteristic of a force that you need to remember. So a force may be considered as fixed vector since it possesses magnitude, direction, and point of application. But in some other cases, forces may also be considered a sliding vector because it will not depend on its point of application. So the principle of transmissibility, which states that a force may be moved anywhere along its line of action, making it a sliding vector without changing its external effects on the rigid body, thus force may be treated as a sliding vector in this case. So an example of that is what I said earlier. If we put a force P right here, so the box will go to the right, it will produce the same effect if we transfer this force right here, as long as it lies on the same line of action, wherein the force will also still, or the box will still go to the right. So meaning the external effect or the effects on the rigid body is still the same. So for our next topic, we will discuss about moment of a force about a point. So there are two possible effects of a force acting on a rigid body. So the first one is the ability to translate, and the second one is the ability to rotate. So in this section, which is, we will discuss about the moment of a force about a point, it is a tendency of a force to rotate a body. So the rotational effect is dependent to the magnitude of the force and the distance of its line of action from the point of interest. So a moment of a force about a point, or shall we say a moment, is indicated by a double-headed arrow as shown in the figure. So it is to distinguish moment with a force which is with a single-headed arrow. Then its direction is also in the direction of the double-headed arrow. The magnitude, in other cases, the moment of a force, especially in two-dimensional problems, is represented with a rotating arrow. Shall we say a rotation like this one? It also may be this one. So it may be counterclockwise and it may be clockwise. So that is depending on the location of the force from the point of application. So the magnitude of the moment, or the how strong the moment is, will depend on the magnitude of the force and how far it is from the point of moment center, or shall we say the point O where the moment or the direction of the moment is being calculated. So if force F and D are large, therefore moment is also larger. Because example of that, if we have a certain shall we say a lever arm, if you want to tie a knot in a certain bolt and you apply a lever like this one, so as you can see, force is applied here and this is the distance. If you want to rotate the knot in the bolt in this direction, so the rotation of the knot will depend on how strong the force is and how far is the distance of the force applied from the knot. So that's an example of a moment. So you want to rotate a certain system so that the effect will be rotation on that body. So from the given figure shown, a force F is acting on a plane and a point O, and a point O is also determined, which is not located. Of course, it's not located on the line of action of the force, because if the force is located on the line of action of, or the force is directed on point O, there will be no moment at that point. So the moment of a force F about point O can be determined using the vector notation. So if we say vector notation, meaning the answer will be in vector form. So the formula for that is the cross product of R and F. R is the position vector from the moment center, which is point O, to point A, where point A is any point on the line of action of F. So meaning, this point right here can be point A, this point right here can be point A, meaning this can be R, this can also be R, because this point A is any point on the line of action. And vector F is the force vector, which is dependent to its magnitude and its direction. So to perform this operation, we need to remember the important concepts and parameters that will guide us in the calculation. So in vector notation, by definition, point O is called the moment center, or shall we say the point where you want to get the magnitude of the moment. So it will be indicated in the problem. Shall we say, if the problem asks what is the magnitude of the moment of force F about point O, so So automatically, point O is the moment center. So the point may vary from time to time. It may also ask, what is the moment of force F about point B? So meaning another point or different point. So this one right here will be R. So it will depend where the moment center is. So moment center, this one right here is the moment center, which is point O. So moment MO is the cross product of the position vector R and the force vector F. So which means MO is perpendicular to the plane that is determined by point O and F. So by definition of cross product. So as you can remember from our definition of cross product, wherein if we perform cross product, shall we say cross product of A and B, so this is vector C. So A cross B by right hand rule. So as you can see, vector C, which is the cross product of A and B, is perpendicular to both vector A and vector B. This is the same in the case of MO, R, and F. So R and F is lying on the plane which is determined by point O and F. Therefore, MO is perpendicular to this plane right here. So that's why there is a perpendicular sign right here to show that MO is the cross product, by definition, cross product of R and F, which is perpendicular to both R and F. Note that the position vector R is directed from the moment center, which is point O, to any point on the line of action of F. So meaning any point on the line of action of F. So you have unlimited number of points in the line of action of F. So in this problem, or in this figure, point A is being shown here as the position vector R, but it doesn't mean that we only have one possible position vector R. We have multiple options in using the position vector R. In problems involving moment of a force about a point, position vector R is not indicated, meaning you are the one who will determine what position vector R should be used. In two-dimensional problems, I preferred, or I suggest that you use the scalar method. So vector method, which is the cross product of the position vector R and F, is very good to use or very useful in three-dimensional problems. But in two-dimensional problems, I prefer you use the scalar method. So the scalar method is simply the product of the force and its perpendicular distance from, shall we say, the perpendicular distance of the line of action of force F from the moment center. So as you can see, this is here, this is D. So D right here is the distance, which is the shortest distance from the moment center to the line of action of force. So it is the shortest because, as you can see, D is perpendicular to F. So if we look at the top view, if this is force, so this is right triangle, so, or right angle, so this is D. So its moment effect is like this. Moment, if this is point O, moment O is equals to F times D. Magnitude of this force times the distance. So most of the two-dimensional problems in statics requires you to calculate the combined or resultant moment. So meaning you have to add all the resulting moment of different or multiple forces, shall we say two or more forces in a certain point. So in that case, the force may have a difference in sense of rotation. So an example of that is in the figure below. So as you can see, we have three forces which is lying on the xy plane as shown. And if we want to get the moment at point O, which is the origin or the moment center in this case, so as you can see, if we use F1 and D1, the moment about point O is F1, D1, and the effect is counterclockwise. Because, as you can see, F1 is going to this direction, and if you check it from this point, its effect is like this. For F2, you have a different direction. So, the effect of F2 about point O is in this direction. So, moment O about F2, which is F2 times D2, is clockwise. Then we have the moment O of F3, which is in this direction, which is F3 times D3 is counterclockwise. So what will happen is that we cannot simply add the values because the directions of the moments are different from each other. So it's like this. It's the same with forces. If we have a 10 kilonewton force right here directed at this direction, and if we have a 5 kilonewton force right here, so if we want to add these two forces, the resulting answer is like this one, 5 kilonewton. Why? Because the direction of this 5 kilonewton is opposing to this force right here. So what will happen is you subtract this 5 kilonewton to this 10 kilonewton force. Instead, if we have the same direction, 10 kilonewton, 5 kilonewton, so the answer if you add this one is 15 kilonewton. So it's also the same with moment. What will happen is that we need to have a certain sign convention to have a distinct direction, or shall we say this distinct sign for both counterclockwise and clockwise direction. So we have in this, the common sign convention is positive for counterclockwise and negative for clockwise. So in this case, we have M1 and M2, M3 I mean is positive and M2 is negative. So if we add the three vectors right here, what will happen is we use F1, D1, F3, D3 as positive, and we have F2, D2 as negative, because the direction of F2, or the effect, or the moment effect of F2 about point O is clockwise. So also note that the magnitude MO will depend only on the magnitude of the force and the perpendicular distance. The force can be transferred to anywhere along its line of action without changing the magnitude of the moment MO, thus treating the force as a sliding vector. So this is also the reason why point A can be any point on the line of action of the force. So what is this phrase, or shall this sentence is trying to say is that if we have a point O and you want to get, shall we say we have a force in this line of action, so say force F, and we know that this is distance D, the perpendicular distance. So the moment at point O, which is force times distance, will not depend on the point of application of the force. If we transfer this force right here, the magnitude MO will still be the same, F times D, because we can transfer this force F at any point on its line of action, making it a sliding vector, without changing the magnitude of the moment, as long as you transfer it along its line of action. So we will have some examples to that so that we can prove this theory, which is what we call the principle of transmissibility. So the direction of the moment is also another important thing to remember in three-dimensional problems. So from the given figure below, the direction of MO, which is 200 Obviously, 200 k Newton meter is positive since the rotation is counterclockwise as viewed from the positive axis. So if we use the right hand rule, meaning your thumb is pointing in this direction, obviously your fingers, the four fingers on your hand will be in this direction or in that rotation. So meaning this one right here is a positive moment. So in that case, the double-headed arrow, which is also the direction of the thumb, while this one is the direction of your fingers, will represent a positive answer because the thumb is directing to the positive z-axis. So this is d distance, and this is f. So f times d is 200 Newton meter. If you want to use the vector method, so we can say r is from this direction is 2j, and f is negative 100 I. So r cross f, the answer will be, if you do the 3 by 3 matrix, so the answer is 200k Newton meter, or shall we say Newton meter. So you will get a positive answer. But if we transfer the force right here, as you can see, the moment effect of that force about point O is in this direction. So using the right hand rule, meaning your fingers, your four fingers is in this direction, what will happen is your thumb will go down, which is something like this. So the answer will be negative. So if you want to try to solve, this is r is equals to negative 2j. Then we have f equals negative 100 I. So r cross f, you will get an answer of negative 200k Newton meter. So that's how you do it if you want to have a better understanding in the direction of moment in three-dimensional force system. So this is what I'm trying to say earlier. So the rotation and the double-headed arrow. So which is this one right here. So if this is your right hand, imagine this as your right hand. This is the direction of your hand, of your thumb. So the fingers will be right here, the four fingers. So this is the same as this one. So this is the rotation of the fingers, and this is the double-headed arrow. So that is the moment of a force about a point, the direction. So use the right hand rule. So we also have Varignon's theorem. So this is a principle of moments, also states that the moment of a force about a point is equal to the sum of the moments of its components about a point. So meaning to that is that if you add these forces right here, let's say we have r, which is f1 plus f2 plus f3 in vector form, we can say that r cross r, which is the resultant force, is also equal to r cross f1 plus r cross f2 and plus r cross f3. So this one right here is still the same, moment of a force about a point, because r has three components, f1, f2, and f3. So we can prove it right here. So MO equals r summation f. So we have, as you can see, the three forces are concurrent at point A, so it's easier to get r, which is common to both the to all the three of forces. So we have r, which is directed from point O to point A. So we can do the distributive property. Then you can add F1 plus F2 plus F3, which is the resultant of the three forces. So let's have first an example for a three-dimensional force system. So for a given figure, Letter A, determine the moment of a force F about point C. And second problem is the perpendicular distance between C and the line of action of F. So, the first thing you need to know is to determine the moment of force F about point C. So, meaning you have to know what is the moment center. So, in this problem, we want to determine the moment of F about point C. So, basically, point C right here is the moment center. So, to get the moment about point C, we need, if we want the vector approach or the vector calculation, we have a formula of R cross F, where F is this force, 500 Newton, but it is magnitude only, so we need the vector approach, and we also need the position vector R. So again, from the previous slide, as I indicated, R is the position vector from point, moment center to any point on the line of action. So in this problem, we have 2 points that is indicated, or shall we say we have coordinates from the origin, which is point B and point A. So we can use 2 possible R. We have this R right here, and we can also use this R. So if we use R from C to A, we can use a position vector R, which is negative 2I. But if we want to use C to B, which is going from this point to this point, the position vector R, remember our previous topic, which is position vectors. So I hope you learned from that, so that we can directly apply it here. So from C to B, we have position vector R is negative 4J plus 3K. So that is in meters. So these are the two possible position vectors that we can use. Actually, we can use a limited number of R, but we don't have the coordinates of these points right here. We only have two known points, which is point B and point A. So in problems involving three-dimensional system, it is more convenient to use the vector method. So this is what I said earlier, that if we have three-dimension problems, we have to use the vector approach because it is more easier and convenient. So to solve the moment of force F about point C, the first thing to do is to decide what position vector R would be used. So as I said earlier, we have 2 possible position vector R that we can use. So in this problem, we can have 2 different values of R. We have the position vector from point C to point A, which is this one. What shall we say RCA, and position vector from C to B. So we already have the values of these 2 position vectors, which we already have here, this one. So in this problem, we can have, or we can use this position vector. Question is, will we get the same answer if we use the second position vector, which is RCB, which is negative 4J plus 3K? So the answer is yes, you will get the same answer of MC, which is R cross F. So if we use R right here with this one or this one, you will get the same answer of moment of C, because the moment of about a force on a certain point will not change even though we use a different values, because the distance of the line of action of the force about point C is will not change in this particular problem. So next is, before we perform the vector multiplication, which is R cross F, we already have the vector notation of R, but we don't have the vector notation of F. So from our previous lectures, I know that you already know how to present or represent a certain force into its force vector or vector notation. So in this case, we have the same formula from our previous lecture, which is magnitude times the unit vector, where the unit vector is the position vector, in this case RAB, divided by its magnitude. So as you can see, RAB, because we have 2i, then we have negative 4j, then we have positive 3k. So that is the three-dimension or the components of the position vector RAB divided by its magnitude to get the unit vector. Then multiply it to the force, magnitude of the force, then we can get the force vector. So to perform the moment of C, which is, shall we say, RCA cross F, so we already have F here, then R is, shall we say, 2i, which is this one. So we have negative 2i because that is from point C to point A. Then substituting, so we have RCA, we have negative 2i, so you have 0 for J and K. Then for forces F, we have the components Fx, Fy, and Fz. So performing the 3x3 matrix from our previous lecture in cross product, so we already know that if we multiply this one, I times 0 times this one, so the answer is 0. J times 0 times this one, so the answer is 0. K times negative 2 times negative 371, so we get positive 742.8. Then minus quantity, 1857 times 0 times K, so we have 0. Negative 371.4 times 0 times I, so that's 0. 278.6 times negative 2 times J, so we have negative 557.2. So simplifying that, we have negative and negative, so we have positive 557.2J plus 742.8K. So if you want to get the magnitude though, you simply calculate this using the given formula. So magnitude is this one. So you get the magnitude of moment C in scalar form, or its magnitude only. So this is calculated here. So remember that for our second problem, we are asked what is the perpendicular distance between C and the line of action of F. So basically, if we draw this triangle right here, which is a right triangle, so this is C, this is B, this is A, so this is direction of F, which is directed from A to B. This is a right triangle, which is this one. So we want to get this distance right here, D, which is perpendicular, so which is that in this direction, D. So what is that distance? So this one right here is 2 meters. This one right here is, which is this one. This is a 3, 4, 5 triangle. So this one right here is 5 from point B to point C. Point B to point C. So if you want to get D, what we can do is, you can solve it geometrically using this triangle, because you can also get this distance right here. This distance right here is square root of 2 squared plus 4 squared plus 3 squared. So the answer to that is square root of 2 squared plus 4 squared plus 3 squared. That is 5.385. So 5.385 meters. So if you want to get that distance D, so you can have similar triangles. So theta right here is also this one. This is theta also. So theta. So we have cosine of theta. Cosine of theta is this theta is also this theta. So I erase this one. This is theta also, this one. So cosine of theta is d over 5. So cosine of theta also in this triangle is 2 over 5.385. So the answer of D here is 5 times 2 divided by 5.385. So you will get an answer of 1.857. So you can use this solution. So we can get D. But there is an easier solution. We can have the formula of M equals F times D. Because we already have the magnitude of the moment from this vector form. You calculate its magnitude, which is this one. Then we also have F, which is given from the problem, which is 500 newtons. Then we can get the value of D. So simple as that. That is easier solution because you have the values instead of solving it geometrically like this one. So in the end, you will get the same answer. So the next one is we will have a two-dimensional problem. So we only have here a one force only. So in this problem, I will prove the principle of transmissibility. Meaning, if you transfer the force in any point, the moment on that particular point will always be the same. So example, determine the force or the magnitude of the moment of force F about point A. So point A right here is the moment center. So this point right here, point A. Using the given figure below, so let's use the scalar method. So using the scalar method, if we use directly M equals force times distance, we don't have the distance here, right? We don't have that distance. So in this type of problems, it's easier if we express the force into its coordinate or rectangular components. Why? Because if we express it into rectangular components, we will have multiple values, or shall we say we have the direct values of D. Example, in this case, if we have point B right here, and this is point A. So as you can see, this is the box. So this is B and A. So this is 6 inches and 4 inches. So basically this is 4 and 6 inches. So if we resolve B into vertical and horizontal component, so vertical is 3/5 of the 200 force. Then we have horizontal is 4/5 of the 200 force. So the answer with this one is 120. This one is 160. So what will happen is this one. So we have 120 pounds and we have 160 pounds. So if we apply force, let's say this is Fx and this is Fy. So the moment about point A is simply Fx times 6. This is counterclockwise because that is positive. Then we have negative Fy times 4. So we will get an answer of 160 times 6 minus 120 times 4. So the answer is 480 pounds inch. So that is positive. So this is counterclockwise. So why is it that my solution is like this? So as you can see, Fx is going to the left and its effect about point A. This is the perpendicular distance. So this distance right here is the same to 6 inches. So force Fx times distance, which is 6 inches. The effect is counterclockwise because this one force right here is counterclockwise. Then we have the Fy 120 pound force is going upward. So this is the distance of the force perpendicular to the line of action of this force. So we have 120 times this distance, which is 4 inches. 120 times 4. So the effect is clockwise because the direction of F is in this effect clockwise. So the answer is 120 times 4. So if you add this one, get the resultant, you will get 480 pound-inch. So that is how the solution is explained here. So we have D1 is 6 inches, this one D2 is 4 inches. So we already have F1, which is 160 and 120. So we have D1 is this one, 6 inches, and D2 is 4 inches. So calculating counterclockwise positive, just always remember the effect of the force, because it's easy to solve, but sometimes it's difficult to understand that the effect of the force is, example for F1 is counterclockwise. So that's why it is positive. Then the effect of F2, which is this force, about point A is clockwise. So that's why it is negative. So the final answer is positive. So meaning the final answer is counterclockwise. Otherwise, if you get a negative answer, that means that the final answer is clockwise because that is our sign convention. Final answer is 480 pound-inch counterclockwise. So to prove the concept of principle of transmissibility, we can transfer this force, this one right here, at any point. If we transfer it here, we have 160 and 120. So this distance right here is 3 inches. So 120 will not have any moment about point A because distance is 0. 120 is passing through point A. So what we will have is 160 and 3 inches. So the moment about point A, obviously, moment about point A of the 160 pound force is counterclockwise. So that is 160 times 3. You will get an answer of 480 pound-inch. So that is the same. If we transfer it to another point again, we transfer it here, 120 and this is 160. So 160 will not have a moment effect about point A because there is no distance and the force is passing through the point. So meaning its line of action is intersecting the point. So we only have 120. So the distance of 120 about point A is 4 inches. That is 4. So the effect is counterclockwise. So the moment about point A is 120 times 4. So the answer is still the same, pound-inch. So this shows that the force in the moment of a force about a point is a sliding vector because it will have an equivalent effect or moment effect about point A even though if you transfer it anywhere along its line of action. So let's have a more complex problem. So in this problem, determine the resultant moment. So shall we say resultant, you have to calculate the combined moment of all the forces present on the system, which is 4 forces acting on the rod about point O, the given figure shown. So about point O. So you can cancel this one out because this force is passing through the point. So we will only have 3 forces left, 50, 20, and 40. So to calculate that one, first, let's start first with 50. So the effect of 50 and its distance first. So if we get the distance, this is the distance of perpendicular distance. So that is 2 meters. So the effect is clockwise. So the moment is 50 times 2. Negative moment about O. Because 50 is clockwise effect to point O and is 2 meters from point O. Next one is 20. So as you can see, 20 this is the line of action of 20. So this is the distance. So this distance right here, if I write it again, this distance is equal to, if you watch this triangle right here, this is 30 degrees and this is 3. So this is D also, which is the same with this one, because this distance right here is also the same to this one. So we have D is equals to 3 cosine 30. So the moment about point O is, I will write it again, negative 50 times 2 for the 50 Newton force. 20 Newton is counterclockwise, so that is positive 20 times 3 cosine 30. Then the last one is 40 Newtons downward, which is clockwise effect. So that is negative 40, and the distance is this distance from point O, which is 2 plus 2 plus this distance right here. So that distance is 3. This one right here is sine 30, because that is opposite to the 30. So let's replace this with sine 30. So 3 cosine 30 is this distance, 3 cosine 30. So this will be the solution to the answer, which is, will look like this. So negative 50 times 2, 50 times 2, clockwise effect. So that's why it is negative. Then we don't include 60 because it doesn't have a distance about point O because it's passing through the point. Then we have 20. This one. So this distance, this is the line of action of the force. This is the distance, which is 3 sine 30, which is, if we look at this triangle, this is 3 sine 30. This one right here is 3 cos 30. So the distance of 40 newtons, which is negative because it is clockwise, is 2 plus 2 plus 3 cos 30, or 4 plus cos 30. So the answer is negative 334 Newton meter. So meaning the final answer is 334 Newton meter clockwise, because the answer is negative.